My name is Walid Rajem. I'm postdoc in Contest Group. And so my goal is to give you like a brief introduction on quantum fields of light. So I will give some basic concept. Maybe for some of you it will be obvious, but still I think it's important to start with good basis. So we all heard about quantum fluids once in our life. For instance, the helium superfluid, like this fluid that below a certain temperature that flows without viscosity, or superconductivity without resistance, or atomic condensate. And what is interesting about this type of system is that they are governed by quantum mechanics, but still you can see some macroscopic effects. You can observe some macroscopic effects. So the question is it possible to have this type of behavior with light? So our common thinking is that light is not palpable. I mean, you cannot touch light, right? So it's hard to see the two beams like bouncing off to each other, not like, for instance, a jet of electron. But actually, two photon scattering is possible, but with a very low probability. It involves 4 vertices phenomenon where you let me just, yeah. So you have like, let's say, one photon going from the left and the other one coming from the right. And you need, so at the same time that these photons can break into electron positron and then they can interact. But when you want to calculate the scattering cross-section, so the probability of this interaction, it turns out that it is very, very small. So it is of the order of 10 to the minus 68 meters square. To give you an idea, it's like the square of the Planck length. So it's really, really small. For instance, if you want like to know what's the cross-section for electron is like 10 to the minus 28. So in the optical regime, it's very rare process. So the question is how we can enhance this photon-photon scattering. So let's come back to the formula of the cross-section. So it's proportional to this term that is important here. So you have like photon energy on top and the particle energy. So in case of free space, so the photon breaks into like electron positron, and electron positron is in the mega electron volt range. But if we go from mega electron volt to electron volt, if we calculate the ratio of the cross-section, we get a factor of 10 to the 36. So it's really a huge gain. So we can expect, instead of working with electron positron, but working with electron hole, for instance, you can expect to observe this phenomenon. Historically, the electron hole pair, exciton, was one of the first to be observed. But I mean, later the people are also investigating like the Rydberg atom or superconducting circuits that have more nonlinear interaction. But one piece is missing. So the photon has no mass, right? So let's imagine like a photon is just a wave, like a plane wave. And it is characterized by what we call the angular momentum, the angular frequency and the wave number, right? And if you plot the dispersion, so the dispersion is just the relation between omega and k. So for a photon in vacuum, you have linear dispersion, right? And the slope of this line is just the speed of light in vacuum, right? So when you have like linear dispersion, you have massless particle. So how we can make the photon have a mass? So we can put the photon inside the cavity. Let's say you have like 2 mirrors, right? So the light is confined in this direction, but it's free to move in the transverse plane. And then the wave number in this direction will be quantized, right? So it's given by this formula where Q is an integer, right? So now the dispersion, so omega of k in plane, right, is just a c square root of k parallel square plus this kz square. So if you're very close to normal incidence, you can do Taylor expansion, and you found that the dispersion close to k equals 0 is the following, where you have like a quadratic term, k square, and here like depends only on the integer and the speed of light and the distance between the two plates. Bottom left, I plotted the dispersion for the photon inside the cavity for the 3 first mode, and as you can see, for like small wave number, the dispersion is quite parabolic, and for large wave number, the dispersion is linear. So you can expect that here the mass will be like 0, but as you approach k equals 0, the mass will increase. And so when you look at the dispersion, so you can deduce the effective mass of the photon inside the cavity, and you found out that the effective mass is given by h bar pi divided by c Lz. And you can know that now, once we have like this photon inside the cavity, the Compton wavelength for the cavity in the photon is now not h bar, it's now a 2 Lz, right? So the distance between the two mirrors give you the Compton wavelength of the photon. So now we have like, we know how to make photon interact with each other, and we know how to make it a mass. So we need one more ingredient, is we need like a strong light matter coupling. So basically, imagine you put some atom like system inside the cavity, so photonic cavity, and you have like 3 parameters that are important. So the first one is omega r, the blue arrow. So it quantifies how much this atom is coupled to the photonic modes of the cavity. You have the gamma relaxation of the atomic system, and you have also the decay rate, so the photon can escape the cavity, basically. And in the case where the coupling between the photon and the atom is very strong, so much stronger than the typical relaxation time of the system, you enter what is called the strong light matter regime, where basically this photon bouncing back is absorbed by the atom and then re-emitted and absorbed and re-emitted before escaping the cavity. And so in this case, you cannot say, okay, we have a photon or atom. So we call it a polariton because it's like half matter, half light. And this way you even enhance the probability that 2 photons interact with each other, because now they are half light, half light, half matter. So now you have the first regime. So it's when the photon, the interaction between the 2 photons is weak, right? So when this interaction between, I will call them polariton because they're half light, half matter, is weak, you can apply what is called the mean field approximation. So it's just, okay, so the interaction is like weak, so you can just average the potential. And this is well described by what is called the generalized Gross-Pitovsky equation, where you have a kinetic term, an external potential, right? A nonlinear interaction term, so the coupling between the 2 polariton, and losses and pumping. So for this term, the losses and pumping, so because we're dealing with photons, so they escape very easily from the cavity. So you need to pump continuously the system, right, to feed it with photons. So it's why we have like a loss term and also a driving term, like a pumping term. And what it's interesting about this equation is that you can describe all the system, even you have lots of polariton, you can describe it by just one wave function. So it's a macroscopic wave function. So you can attribute to this system like a macroscopic effect. let's say now you pump your system with like resonant pump, right? So you pump, so you create two polaritons with the same momentum from the pump. And these two polaritons will interact, so they will bounce, and then you will have like at the output two other photons with different momentums. And this is an example of the polariton four-wave mixing. And so I'm showing this because it's to make an analogy between nonlinear medium, right, and this strong light matter coupling. And if you replace the G, right, the complete constant B, two polariton with the chi3 of a linear medium and the photon by the polariton, you can have effectively a nonlinear medium. So effectively you have a nonlinear medium. And you can also pump the system not at resonance, right? So you excite way above, so the resonant excitation, the resonant energy, sorry. And so left is the dispersion of the polariton. And what happens is that you can excite the polariton like at high energy, and then it will relax. And this gives rise to what is called photon Bose-Einstein condensate. And Iacopo will show you nice images from experiment showing this photon condensation. So this was for the weak interaction, but you can also be in the regime of a strong photon-photon interaction, right? So a nice example to understand this concept is just by taking like an array of single mode cavity. And this cavity talks to each other, so you have some field overlap. So you attribute like a hopping term, J, between two neighbor, two next neighbor single mode cavity, and some interaction, on-site nonlinear interaction. And this is described by what is called the Bose-Hubbard-Hamiltonian. And again, so we are continuously pumping the system to feed the cavities. So it's why there is this dissipative, driven dissipative term. And so again, so we have like this hopping term between two sites to a next site. You have like inside interaction, so it involves multiple photon coupling, and you have like the pump here. So this type of system of strong interaction has been implemented, for instance, using an array of defect photonic crystal cavity, where at each site you have an atom, or like a Rydberg atom, for instance. Or you can, it has been also implemented by superconducting circuits that shows strong nonlinear interaction. And one interesting, I will end up with this slide. So one interesting fact about this, when you have like a strong photon-photon interaction, is that when the on-site energy, right, the U, is much larger than the coupling between two sites and also the loss rate, you can have what is called photon blockade. So the way I see the photon blockade is that you have the two photon states. So for instance, if you want, you put one photon inside the cavity, so then it will change the energy level of the two photon state, right, by an amount of U. And effectively, so what happens is that once a photon is inside the cavity, another one at the same energy, so at the same resonance of with the cavity, cannot enter the cavity because it will not be at the resonance with the two photon state. And so effectively, you can have an impenetrable photons. So that's why you call a photon blockade. So you cannot have no more one photon. You cannot have more than one photon in the cavity. Okay, so this is the end. So now, if someone has questions, or I can start. So now I will let Iacopo present.
Maybe you
so
can.
I will, yeah, exactly. This is what I was about to do. So Iacopo Carusotto completed his PhD in 2000, right, in Scuola Normale Superiore in Pisa, Italy, and then carried out a postdoctoral work at Laboratoire Kastler-Bruxelles in Paris. And since 2003, he has been researcher at the CNR BEC Center in Trento, in Italy. And he has been associated researcher for CNRS in France, right? And a visiting professor for the Swiss Federal Institute of Technology, ETH, in Zurich. His primary scientific interests include quantum fields of light, from superfluid light to strongly correlated photon gases, topological photonics and physics, and the study of analog of gravitational phenomena in atomics and optical systems. So the stage is all yours, Iacopo.
Okay. Thanks a lot, Walid, for the introduction. Thanks also to Boubacar for the kind invitation to be with you. I really hope to be able to be in presence in Berkeley in the next future at some point. So it would be really very much looking forward to discuss with you all in presence. For the moment, I will try to just to tell you something exciting online on these quantum fluids of light that Walid has nicely introduced in his introductory talk. And let me move to my slides. Here we are. Okay. Can you see the slides?
Yes, we can. Yeah.
Very good. Perfect. So the idea is to give a presentation today of this wide field of quantum fluids of light, which encompasses a lot of different avenues for contemporary research, where this general idea is having very exciting results and even more exciting perspectives for the next future. So it's an adventure that started kind of 20 years ago, more or less, but is still giving more and more intriguing results and exciting advances. So Walid has already told you what is the idea of a fluid of light, so I don't need to go through all these. And in the first part, just a couple of minutes, I will try to just summarize what are the big achievements of this field in the last, say, 10 to 15 years. So Walid has mentioned these experiments under incoherent pumping, which basically have brought this niche physics of polaritons to real the first page of the scientific news, with the observation of Bose-Einstein condensation of light particles like photons or polaritons. So on the top row, you see this is the diagram of how these photons are pumped in a suitable semiconductor structure. And here in this central panel is the experimental image, which first gave a strong and undoubted evidence of Bose-Einstein condensation of photons in a planar microcavity, where photons acquire mass because of confinement, as Walid has told us, and they interact with each other via the nonlinearity of the cavity medium. So in this way, just by pumping hot photons in the system and letting them to relax by dissipating the extra energy into the surrounding material, the experimentalists in Lausanne observed that for low pump intensities, which mean low density, the photon distribution is a wide one, basically a thermal gas. But by pumping stronger and stronger, a very narrow peak appears in the momentum distribution, very similar to the one that was observed in the first atomic BC. So then, of course, one had to check the other characteristic properties of a BC, like interference, which was measured here in this experiment by Max Richard in Grenoble, then quantized vortices, and then suppressed fluctuations in this photon gas. Still, while the previous slide I showed you the typical signatures of BC as one learns them from textbooks. Here, very early experiments realized that the shape of the BC, for instance, is very much dependent on the size of the pumping spot. Going from a standard momentum distribution, which is peaked around k equals 0, as it happens for a wide spot, to something completely different, which is basically a BC with a momentum distribution localized on a ring at finite momentum, which occurs when the pumping spot is very small. So this is a very strange phenomenon for all those who have some familiarity with standard statistical mechanics, where it's known that the condensate typically appears in the lowest energy mode, which is available for single particles. Here instead, the system, the photonic system, being intrinsically a non-equilibrium system, where one needs to continuously pump excitations with some external laser in order to compensate for the emission of light from the condensate. So the condensate, which is here in this pink area, is a driven dissipative object which arises and whose properties are determined by dynamic balance of pumping and dissipation. So it's not an object which is necessarily at thermal equilibrium. So its properties can be very much different from the ones that one typically expects for BCs. And in particular, a quantity as simple as the momentum distribution can get dramatically modified by this non-equilibrium condition. Of course, seeing just a ring of modes being occupied is not really a proof of condensation. It may be just some thermal state with a crazy momentum distribution. But actually what Max Richard did was to make the different parts, different components in K-space to interfere with each other. And indeed, he showed that these components are mutually coherent, which shows that one is dealing with a single condensate which is spread over many modes at a given magnitude of K, but with any possible angle along the cavity plane. So this is an example of peculiar behavior of these non-equilibrium BCs of light. Then there's been other striking experiments around in the 2008 by the group of Alberto Bramati in Paris, who gave the first evidence of superfluid features in these photon fluids. Basically, the idea is just to take a fluid and move it in some direction. In these graphs, it's moving down at different speeds, say at different ratios of the flow speed over the sound speed. Here in the left, the blue panel is for a low density for which the speed of flow exceeds by far the speed of sound. So in this case, the flow which goes downhill, downwards, hits a defect which is here localized at this point. So the fluid is able to scatter on this defect and be diffused in all directions, creating these fringes, which is basically what happens normally when a river hits a rock along its path. A lot of waves are created in the river by the interaction with the rock. If instead the density of the fluid is very large, then the speed of sound gets larger than the speed of flow, and one is in the regime of superfluid flow, which is characterized by the fact that the defect is not able to create basically any perturbation in the surrounding fluid. So actually what happens is that the fluid comes from the top, goes around the defect and keeps flowing downwards as if nothing had happened. So the defect basically is not able to create any perturbation in the fluid, like an impurity which is present in, say, liquid helium, moving impurity which does not feel any friction by the surrounding fluid. And here is a demonstration of this property for a fluid of light. Very recently, this idea of Bose-Einstein condensation of light has got a new impetus by the observation of the so-called topological lattice, topological lasing in two-dimensional lattice. Basically, this is a lasing phenomenon where photons accumulate coherently in an edge state of a topological lattice, which can also be seen as Bose-Einstein a non-equilibrium Bose-Einstein condensation of photonic particles into the single particle states which are on the edge of a topological lattice. Being a non-equilibrium phenomenon, there is no reason to occupy just the ground state. And indeed, with some care, people have been able to make these photons to condense on the edge state. So in the first part, say it's part 3, but it's the first part of the new results in this of my talk. I will bring you across a brief journey through the early days of topological photonics and showing you what are the basic ingredients of this field and how this was used to open a new world to condensation, non-equilibrium condensation phenomena. Very good. So you may argue that all the topological physics that you learn from condensed matter is typically based on interaction of electrons with some magnetic fields. So, and the fact that the photons are neutral does not permit to observe this physics with light. This is actually, there was another platform which got very popular for studies of magnetism for neutral particles, which namely the so-called synthetic gauge fields for atoms. And basically the idea is to dress atoms with suitable combinations of Raman optical beams, static magnetic fields, and other optical tools in a way that atoms effectively feel a magnetic field when moving in space. So even though atoms are neutral, by dressing them with other electromagnetic fields, one is able to endow them with some effective charge responding to some effective magnetic field, synthetic magnetic field. So here in this slide, there are some examples of this physics as it has been studied in the last decades, starting from pioneering work using the synthetic magnetic field, which is associated to the Coriolis force when an atomic cloud is put into rotation. Here, other experiments with Raman magnetic fields, showing the nucleation of vortices by this magnetic field, by sort of like vortices in a superconductor at high real magnetic fields. These other experiments in lattices, where one either shakes a lattice and obtains a so-called Floquet topological insulator. And here is a laser-assisted doping in a lattice where jumping from one side to the next is associated to absorption and remission of some suitable laser beam, which then imprint a hopping phase to the tunneling process from one side to the next. And here in the bottom right, there is one more idea to generate not only synthetic magnetic fields, but even synthetic dimensions. So rather than working with just the physical dimensions, these ideas allow to go to higher dimensions. People have gone in this way up to 4 dimensions. Good, but this is beyond this talk. So with this idea of synthetic magnetic field in mind, there is a new field of research that basically started in around 2008 with these pioneering papers by Haldane and Raghu, who basically realized that all the physics which is behind the integer quantum Hall effect in electrons in solids basically depends on the geometrical properties of block bands, which are a concept which refers to the wavy properties of electrons and not to their fermionic nature. As such, there is no reason not to observe similar effects related to integer quantum Hall effect using the photonic waves in suitable solids for light. So solids for light take the name of photonic crystals. So these are basically periodic structures of magnetic and electric elements which create an effective potential for photons, to say it simply, and as a result, complex band structures for photons in this periodic medium. By breaking time reversal in a proper way, one can obtain non-trivial values for the so-called topological invariants of the system, which are the quantities which are related, for instance, to the transverse conductivity and to a quantization of transverse conductivity in an integer quantum Hall system for electrons. So by designing in suitable way the lattice, one can obtain a non-trivial topological invariance and then try to observe topological properties analogous, for instance, to the quantization of the transverse conductivity of electrons in strong magnetic fields. Of course, for light, the concept of conductivity is not really well defined, but still in this paper by Haldane and Ragu, they had the idea of not looking at the conductivity, but to look at the one-way propagation of light along the edge of the system, exactly as it happens to edge state for electrons on the edge of a quantum Hall system. So the first experiment was done at MIT, a group of Marin Soljacic, who basically built a topological crystal by assembling a periodic array of magnetic elements in between two metallic plates, so to have an effectively two-dimensional periodic, two-dimensional photonic crystal with magnetic properties. Magnetic properties are needed in this realization to break time reversal. In this way, the bands, which are plotted here, have some non-trivial topological number, topological invariants. For instance, the first one has 0 topological invariant, but the first one has 1. So above this second band, there exists a topological edge state, which lives in between the two bands and propagates in a one-dimensional, in unidirectional way along the edge. So in these two plots, I give you a bit more feeling of what it means having a unidirectional edge state. So basically, in crystals, there are some allowed bands and a forbidden gap in between, like in solids, between the valence and conduction bands. And in a topological system is characterized by the presence of some edge state, so a state which lives on the edge of the system, which propagates in a unidirectional way. Which means that if I put an antenna A at a frequency which corresponds to the gap, for instance here, this antenna will not emit a spherical wave around it, but it will only emit waves which propagate, for instance, to the right, because this edge state is propagating to the right. And why it's not going to the left? Basically, it's because there exists no state going to the left. So if I put a defect on the road of this light cannot be reflected, it happens normally, but it is forced to go around the defect because there are no modes where light can be scattered back. So as a result, the presence of a scattering is just perturbing the flow of light, but is not inducing any backward reflection. Conversely, if I put an emitter at antenna B, light will not go back, but will keep propagating to the right. So as a result, there is propagation from A to B, but not from B to A. This is a sign of no reciprocal behavior, which is of course forbidden by the Lorentz reciprocity theorem in media which do not break time reversal, but there is no reason for it not to be violated in these T-reversal breaking media. And these are the experimental results obtained in this paper, where basically people looked at the transmission from A to B, and they saw that an effective transmission was taking place, while from B to A, there was absolutely no transmission, which is exactly the signature of having a non-reciprocal behavior on the edge of this topological photonic crystal. So this was the beginning of this adventure of topological photonics. The first experiment that I showed was in the microwaves. Then in the coming years, there has been a lot of pressure from the community to try to see these effects for visible photons. The problem for visible photons is harder to have magnetic materials which are strong and well performant. So the amount of magnetic response is much weaker for visible light, which means that observing topological phenomena is more difficult. Here are the first two experiments reporting this kind of results. This is a Floquet topological insulator for light, and this is an example of spin-all device which does not rely on having magnetic elements. It goes around this need by making two copies of the same photonic system with opposite chair numbers, and then just looking at one of the two copies with a supertopological pumping. So these kind of devices allowed for the observation of the first imaging of this topological edge state. Here was images from the Mamada Fetzi's group, where basically an input was put here, and they saw light going down in a unidirectional way around the defect and then keep going along this edge. Even if the pumping was here, nothing was going on the opposite direction. So it was really a unidirectional propagation. That's the experiment, and that's the simulation results, where there is an excellent mapping between the two. So this experiment was done, as I was saying, on a silicon photonics platform, which is very interesting in view of technological applications, as it does not need to include any magnetic element, which is a very practical thing for long-term applications. Then the next question that the community started wondering is what happens if one adds some gain to such a topological model? The very first reports were obtained in the group of C2N by Philippe Saint-Jean and co-workers with Alberto Amo and Jacqueline Bloch, who used a one-dimensional geometry, where this topological lasing occurs on a mode which is on the edge of a 1D chain, which basically is the edge of here is a mode which is localized on the last few pillars. But the things are much more interesting if one goes up in dimension in a 2-dimension, like these other two experiments. This one by Boubacar's group when he was still in San Diego. And this is the group, a competing group in Haifa at Technion with the first author, Miguel Bandres, using two different platforms. So the first experiment by Boubacar used some 2-dimensional photonic crystal, including some magnetic elements and putting the system under strong magnetic field. The gap was kind of small because of the small magnetic response of any material in the visible or near infrared, but was enough to see a nice topological photonic mode which got lasing and leaving around the shape of the system, which had the kind of United States shape here. So here is a sketch. The mode goes around in this direction and then exits along this extra waveguide, which is built in the system just to collect the laser emission. Soon after, there was this experiment in Haifa, which used a sort of Hafezi platform, supplemented by this TIG element, which is a S-shape element in the cavities, which is needed to stabilize the system against a pseudo-spin symmetry, which may disturb the topology. This is a detail, important detail, but goes beyond this talk. So this is a system which embeds some magnetic elements, so explicitly break T reversal. here is another symmetry of the system, has other properties. Is a system which preserves at linear regime time reversal, but time reversal is broken in a dynamic way because of the nonlinearities intrinsic in topolaser application. We can discuss all these details if you're interested in the final part of this meeting today. Good. So I'm a theorist, so I have a lot of experimental friends, but I myself am a theorist. So my natural question was to see what can be interesting in making the topological lasing in these two-dimensional models. What new physics can be studied in these systems? So actually, one of the main reasons pushing research in these systems is to answer one technological need for high-power devices emitting coherent light with a semiconductor platform. Normally, if you take a semiconductor laser, in particular a VCSEL, for instance, and you want a lot of power, you have to make the VCSEL very big. The problem of having a VCSEL very big is shown in this picture. It lasers everywhere, so you have a lot of power being emitted, but the different points which are emitted are often not coherent with each other. And often the emission is even multi-mode, which can be fine if you just need a laser pointer, but perhaps it's not enough if you want to use a laser, for instance, for meteorological applications or as a source of coherent light to do some lithographic application. So it's crucial importance to have a system which is able to preserve coherence over a large surface. So having a system which is large enough, this is say 25 by 25 sites, considering that each site can be a few microns, is an object which can start being a macroscopic one. And so why are these topological lasers promising in this direction? So basically the idea is that the motion of the edge mode around the topological laser, which goes around the system, keeps going without being scattered back. So whenever there is some two sites emitting, the emission from the site which is upstream will eventually go to the site which is downstream. So this exchange of light field enforces the coherence between the different sites. So in this way, the different sites participating to the laser emission in a topolaser get phase locked, which means a massively coherent emission, which is completely different from what happens in this standard topologically trivial system, where the emission at the different areas basically stays localized, don't communicate with each other, so they stay phase unlocked. These are a bit of blah, blah, blah. Things have to be put into a bit more serious mathematical terms. So this is what Matteo Secli did in his master thesis, and Matteo will, I think, join Berkeley in a few months from now as a postdoc. And what he did in his master thesis with us in Trento was to do some numerical simulation of this edge mode as a function of the disorder applied to the system. And basically what he saw is that for moderate disorder, where the disorder is already a significant fraction of the gap, but not so huge, still the emission is very nice along the edge. There are a few disturbances, but the emission is still a single mode one. Is again the comparison with what happens with the disordered system. So this basically means that the coherence, the mean field emission, remains robust even if some disorder is put in the system. And this result was basically obtained simultaneously by Matteo and by the group in Haifa, and is reported in this theoretical paper. Good. But of course, a mean field theory, which is basically classical electrodynamics, is often not enough to quantify the coherence of a light emitting device. It's important to quantify the coherence of this emission. And this was the goal of Ivan Amelio's PhD thesis, whose activity consisted in simulating with some stochastic field method the dynamics of the phase of a topolaser device, like the one here in this picture, to answer to the question, what are the ultimate limitations to coherence? Actually, following what other people had done in the last years, including Hud Altman with Sebi Dil, Vladimir Gladilin and Michiel Wouters, Leonie Canier and Anna Minguzzi in Grenoble, different groups have realized that the emission, the dynamics of the phase of a laser device follows a non-equilibrium statistical mechanics model, which is very well known in that community, which goes under the name of Kardar-Parisi-Zhang model, where Parisi is this year Nobel Prize, our colleague from Roma University. And actually, what these people realized is that there are some specific scaling properties in the coherence function of a laser emitting in a spatially extended way, where basically the coherence only depends on a combination of time and position. In a sense, what we are looking is the G measured at the distance x and at the time t. It only involves this combination with a characteristic KPZ exponent of 3/2, and all the curves at the different positions collapse onto universal curves. This result is a very general result of spatially extended lasers, and also applies to topolasers, as Ivan has demonstrated, where basically the dynamics of the laser mode on the edge of the system is an effective one-dimensional field. It follows the KPZ temporal scaling and has some crucial advantages from the fact that it has intrinsic periodic boundary conditions, because any sample which is finite size has a finite boundary with periodic boundary conditions. As a teaser, there's been very recently experimental evidence of this KPZ physics in condensates of light, and the manuscript will come out very soon by Quentin-Fontaine at C2N. It's a wonderful experimental verification of this physics. So to go back more deep into this coherence, there is one thing that Ivan realized, is that this effect of having an extended laser satisfying KPZ physics means that the line width, the minimal line width that a laser, a spatially extended laser, can have, is not only determined by the well-known Bogoliubov-Charlotte-Towns line width that one learns from standard quantum optics textbooks, but has some corrections in the sense of reducing the characteristic time due to the KPZ features. So for a small size of the system, the characteristic coherence time scales with the size, with the photon number, as we all learned in basic quantum optics courses. But for large enough systems, the scaling goes from linear in the number of sites, so number of photons, to something which grows most likely as 1 to the 1/3. Ivan has some theoretical model to explain this, and at some point, some paper by him will come out to explain this 1/3 with this kind of very unusual 1/3 behavior for large distances. But okay, this result is a sort of negative result, which says that the coherence of a spatially extended laser suffers from strong limitations. But there is one point which makes topolasers the ultimate laser source if one wants to avoid the problem of disorder and keep a high coherence and high power. So these are numerical simulations for the coherence calculated in the presence of static disorder. which is something which is basically unavoidable whenever you build a laser. Whenever you have a semiconductor device, the sites will not come out from the fab exactly identical. So there will be some inhomogeneous broadening, some random disorder, which on a standard non-topological laser means that the emission at the different points in the lattice will be at a slightly different frequency, which in other words means the emission is strongly multimode. Here is instead the emission for a topo system, like the one that Boubacar has, where the coherence is spatiotemporally extremely robust, one has a very strong single mode emission, whose coherence time drops as a function of noise, half disorder, at a ratio disorder of band gap, which is extremely large. More or less, the characteristic time, so the coherence time remains the one of a clean system up to the point where the topological gap is broken. So a posteriori is a kind of trivial result that disorder does not make any harm to a topo system until it closes the gap. The importance of this work by Ivan is that he was showing that this same conclusion not only holds for the mean field dynamics of the coherent field, but also holds for the quantum fluctuations which unavoidably exist in any topological laser device. So this result is extremely promising in view of using these topo lasers as the ultimate light source if one desires strong intensity together with high coherence. So then the ball now is in the camp of our experimental friends to actually verify that our theory is meaningful, and then to develop better and better topo laser devices for different kind of applications. So the world is really open to great adventures in these directions. Good. So this is more or less all I wanted to say about weakly interacting fluids, which can be described by in terms of, say, Bose-Einstein condensation, weak nonlinearities, equations like Gross-Pitovsky equation, or if you prefer, Lambda semi-classical theory of lasing, which are basically equivalent in this context. What I'm going to show in this second part of the talk is some future in the sense of strongly interacting fluids of light, where photons interact a lot with each other and are, for instance, in the photon blockade regime that Walid was presenting us before, which basically means that two photons cannot sit on the same side of a lattice because the nonlinearity is so strong that the presence of a single photon is able to shift the cavity frequency by a strong enough amount that the second photon is no longer resonant with the transition, so it cannot enter. As a result, the photons are effectively impenetrable particles, which, by the way, is a completely opposite regime compared to what we learn in any course about Maxwell equations, where photons or electromagnetic fields are linear objects. So, in our context, the most intriguing stuff is when we combine these impenetrable photons with a strong synthetic gauge field for light. In the regime, one can expect to observe the analog of a fractional quantum Hall effect for photons. Here was some very early simulations by Unur Umujalila, who at the time was postdoc in Trento and now he's professor in Istanbul in Turkey. And actually he proved that with suitable pumping of the system, one could find spectral signatures in the absorption and transmission spectrum of such a device, which correspond to the fractional quantum Hall states. So these ideas were put into practice by a group in Chicago, by John Simon and co-workers, who actually had a much smarter idea about how to realize the device in practice. Much simpler system of just 4 mirrors in a ring cavity setup, which is not planar, So a three-dimensional twisted cavity where the solid angle encompassed by the motion of the laser direction in space is able to induce an effective magnetic field for light. In this way, the guys observed the lambda levels for photons, and in presence of Photon blockade, they were even able to see some specific features in the spectrum which correspond to a two-photon Laughing state. So basically, how to recognize that this two-photon state is really a Laughing state? What John and co-worker, Logan and Nathan and other co-workers, basically, they were able to see some spectral feature in the transmittivity of this cavity setup, which is shown here, which is at some specific energy and correspond to a state which is two photons in the state with angular momentum 6 plus plus a state with one photon in 3 and one photon in 9. And the structure of this state, which seems very innocent, is exactly the same as the one of the Laughing state for two particles in a fractional quantum Hall state of filling 1/2. So in order to check that this was indeed the state, basically what they did was to make some angular momentum tomography of the state, and they found that there is a strong positive correlation between photons being in the state 3 and the state 9, as indeed follows from this writing, while the photons in the state 6 show some anti-bunching, because basically they are a sort of Fock state with two particles, where the correlations are reduced by 1/2 compared to a coherent state. So just by making this tomography in angular momentum of the light transmitted from the cavity, John and co-worker were able to assess that the state they had in the cavity is the two-photon Laughing state, which is the baby version of a fractional quantum Hall state for light. So now the challenge is to obtain fluids which are larger and larger. Unfortunately, the scheme they used, which consisted in using a coherent source of light with a given angular momentum, this does not scale well with increasing number of photons. So in order to access larger particle numbers, one has to resort to completely different pumping schemes. An idea which got kind of popular is to use frequency-dependent incoherent pumpings, which basically means using laser-emitting media, which are very narrowband. So instead of using standard amplifying media in solid state, which has very broadband, TISAF is perhaps the most extreme example of very broadband amplifying medium. Here we want exactly the opposite, to have a medium which is able to inject photons in the system on this green transition, but above a given target state, we are not able to inject any more photons. In this way, the population in the system will accumulate in this target state. Is indeed here, no more photons can be injected, and if the system decays down, the only way that it can be repumped up is to go back to the target state. So spontaneous emission will include a bit of population on the lower states, but this will not exit from the manifold of fractional quantum Hall states in our language. So this idea has not yet been implemented in the presence of synthetic gauge fields to obtain fractional quantum Hall states of large size, but it underlined the experiments by Alex Ma and co-workers in the group of John Simon again and Dave Schuster in Chicago, who used a circuit QT platform to observe the first many-body state of light of the form of multi-insulator. So a multi-insulator is basically a system where each site contains one particle, and no site contains more than one particle, and no site is empty. So it's a completely uniform distribution of photon in the system. And this is exactly what happened here. Each of these sites in the circuit is a lattice site, and basically with a suitable pumping, they were able to stabilize a state which contains one photon per site. So every time one of these photons is lost, it's immediately replenished by the pumping system, but the pumping system is not able to inject a second photon in a site if already one is present, because this would cost some energy. And the energy basically brings the system out of resonance in our blockade idea. Out of resonance, in our case, from the pump laser beam. So in this way, John and Dave were able to observe effective multi-insulator of photons, which is the first example of many body state with light. Then calculations, again by Onur, showed that the same idea indeed works also for fractional quantum Hall states. And basically, he was able to show that the fidelity to the fractional quantum Hall state can be quite large, of the order of 0.8, even 0.9 for supertable parameters, provided the pumping is chosen in the right way to concentrate all the population in the laughing state. So in this way, we hope that in the next future, we will be able in the lab to obtain fractional quantum fluids of light of a large number of particles, which would be a very interesting platform to study many-body physics in a completely new point of view. What could be one of the questions that these systems could help answering? It could be to probe once for all the anionic statistics of quasi-holes in a fractional quantum Hall system. There is in electron systems a very strong evidence of the fractional charge of electrons, while the evidence for the fractional statistics is a bit more elusive. There are some strong evidence that something of this form is happening, but there is no real final answer with real and conclusive evidence of the exchange statistics. So here the idea is to try to use these photonic systems to provide this answer. So fractional statistics of two quasi-holes in a fractional quantum Hall means that when I take two such quasi-holes and I exchange them, I don't get the plus factor that occurs in bosons. I don't get the -1 for fermions. I get something completely different, which is e to the I phi braiding, where phi can be a generic phase, which is characteristic of the system. For instance, a fractional quantum Hall 1/3 with elections, it will be 2 pi over 3. And if it is a bosonic one, it would be pi over 2. So this gives a very peculiar signature. So in a photonic system, one can imagine doing exactly the same, creating two repulsive potentials in the trap, for instance, laser beams, and then braid one on the other. This would introduce a macroscopic many-body Barry phase to the quantum state, which is visible as a shift in the transmission resonance from the cavity. So this would be a kind of direct way of observing this many-body Barry phase, but it requires having thin objects which move through the fluid, which often is a bit impractical. So what Onur realized in a completely random way, we're discussing other stuff when he realized about this very important connection between the braiding phase of two quasi-holes, one located at the center, one off center, and the angular momentum of the photonic cloud. And so basically rotations are the generator of, angular momentum is the generator of rotations. So it's natural to think that it's connected to the phase that the system acquires when one quasi-hole goes around the other via rotation. So by doing some math, you realize that the angular momentum can then be related to this braiding phase. And this angular momentum, in turn, can be measured from the size of the cloud in time of flight, in atomic language, or the far field image of the cloud in the photonic language. The problem of this scheme is that it requires a very high sensitivity in the angular momentum, which can be very difficult in experiments. So what Elia then realized was that these same angular momentum arguments can be extended and reformulated in terms of the density in the cloud, in particular the density around each quasi-hole. So by comparing the density depletion of single quasi-holes and the ones of a double quasi-hole, and taking some suitable difference of the two, he was able to infer a mathematical relation between these quantities and the braiding phase of the two anyons. The advantage of doing this measurement, which is in the bulk, is that it only depends on the inner part of the cloud. So whatever is happening on the edge, which typically is excited by thermal excitations, does not at all enter into the calculation. So the statistics is only related to the bulk, which can be observed with a very good precision, since the fractional quantum Hall fluid is an incompressible fluid. So by applying this method to some quantum Monte Carlo simulations, they were able to find exactly the expected braiding phase. Here, the calculation is done for an even more complicated quantity, even more complicated quantum state, which is not an abelian fractional quantum Hall state, but is even a non-abelian one, where the phases of braiding have completely crazy numbers, like 1/8 and 5/8. Having these crazy values means that the algorithm really works, because it would be kind of strange to find such strange numbers exactly when they need to be there. So the interest of this proposal is that it can be directly realized in the Chicago setup, just by adding to their setup some localized repulsive potential, which pins quasi-holes at the different positions in space. So as soon as the guys will be able to create a quantum fluid which is large enough to accommodate several quasi-holes, it will be relatively easy to infer the anionic statistics of quasi-holes. Here is another similar calculation done not for the cylindrical trap of in Chicago, but for a lattice of sites, which is more related to circuit QED platforms, and the numerical calculations done with the 3 tensor network ansatz, which was a tour de force from the numerical point of view, gave exactly a very good convergence of the result for the braiding phase to the expected pi value of anionic particles, which means that this kind of experiment is accessible also in state-of-the-art circuit QED systems, like the ones, for instance, at the Google Labs in Santa Barbara. So doing all this measurement would answer to one of the most hottest questions in present-day quantum condensed matter, which is to obtain a final evidence for anionic statistics of quasi-particles in 2D. So since I'm running out of time, let me move to the conclusions of my presentation, whose aim was basically to convince you that these fluids of light are a wonderful platform to study new many-body physics in different contexts, from BC in topological edge states to strongly correlated many-body physics of fractional quantum Hall or multi-insulator physics in completely new non-equilibrium context. So for topological lasing, we have already seen a lot of promising optoelectronics applications, which are nowadays kind of quite clear in the community. What is more speculative is how these strongly interacting photonic systems have very strong perspectives for quantum technologies. Since I'm speaking to a quantum computing audience, I wish just to share with you some crazy idea, which is somehow guiding my thinking in the last year or so, which is basically to use these quantum Hall fluids of light as a platform for topological quantum computing. Hopefully more performant than, say, Majorana in solid state architectures or 5 halves fractional quantum Hall states in electronic gases. So, of course, this is a platform which has to be built from scratch, but who knows, it may have some very useful advantages in this perspective. So the idea is that one knows that fractional quantum Hall fluid, when they are built in topological non-trivial geometries, for instance, tori or tori with multiple holes or other crazy boundary conditions, they can have so-called topologically degenerate ground state, which means that topologically degenerate means that these states, the ground state, consists of several states which are degenerate in energy and are not mixed by one body observables. So whatever trivial observable you can build, say position of one particle, momentum of one particle, does not give any which way information in which of the different states of the topologically degenerate ground state one is living in. So simple measurements are not able to mix these two states. So any quantum information which is stored in superpositions of these states, this topological degenerate manifold, will be preserved by this topological insensitivity to trivial operators. So to say it in optical terms, you know that if you build a Schrödinger cat state with coherent state in alpha and minus alpha, this state is extremely fragile against losses. Just detecting a single photon will project you on the plus alpha or the minus alpha state. This because dissipation provides a which way information, and then you basically destroy the Schrödinger cat. This does not happen in these topological systems because losing one particle basically provides information on the one body observables. But those theorems of topological degeneracy say that one body observables cannot give you any which way information on the different topologically degenerate ground states. As a result, losses are not disturbing this encoding of quantum information. So one can encode the information in a topologically robust way. When you lose one particle, is no problem. You can refill it, and this refilling will not disturb the topological encoding of quantum information. What can disturb this encoding is when you lose one particle. This one particle is fractionalized into several quasi-particles, and these quasi-particles go around in the system and are randomly braided around other quasi-particles which were by chance already present in the system. If this happens, you're dead.
Iacopo, maybe we should stop and we can discuss some of those during the discussion part, if you don't mind.
Yes, sir, no problem. Just
Okay.
for realisticity of what I'm saying, on the top right, there is a sketch of an experimental realization of topological system in a Mobius band, just to show that these things are not so crazy. Good. So this is a kind of speculative perspective, and thanks to all of you for being here, and I'm looking forward to hear your questions.
So thank you, Iacopo. I think this was a very exciting talk, and also thank you for sharing your perspective on how these ideas could contribute to the ultimate creation of the construction of a quantum computer. I really enjoyed that perspective. So, so the stage is open for questions. So please go ahead if you have questions. Just unmute yourself and go ahead.
Hi, Iacopo. Thanks for the very nice talk out here. So In the first part, you mentioned that you made some remarks about quantum fluctuations for the weakly interacting case. I was wondering if you could elaborate on that. You mentioned first order coherence, characterization of the G1 function, but are there other signatures in second order coherence or squeezing that would kind of be more directly related to quantum fluctuations beyond kind of the first order coherence in the system?
This is a very good question. Thanks, Alp. So the second order coherence, say intensity noise, typically in laser devices is not very interesting. It's basically flat because you have reduced intensity fluctuations in a laser. So basically G2 is equal to 1. Squeezing could be a very interesting thing to look at, because there could be squeezing between the different sidebands of this emission. And this squeezing may have some interesting role and interesting application, for instance, to obtain a comb of correlated modes. That's a path which is worth exploring, but for the moment, there has not been much literature on this, except for instance, for the correlations which are present in the equilibrium state when you coherently drive the system, where the steady state has the form of a thermally excited Bogoliubov vacuum. So it's a squeezed vacuum plus some excitations. So there is none, but there are not many experiments having proven the properties in good detail. I would say one of the best experiments showing these squeezing features was obtained by the group of Cantin-Glorieux in Paris not many months ago on a fluid of light on a different platform. There they showed some very interesting squeezing-like effects. It's Cantin-Glorieux, it's an experiment about, they call it dynamical Casimir emission, because it's the same kind of quantum fluctuations as in dynamical Casimir.
So when you mention quantum fluctuations in that first part, you're mainly referring to the G1.
Mostly the G1, yes.
Okay.
Which is actually the one which is of easiest experimental interest for devices.
Okay, thank you.
I have a very general question. So basically, you mentioned these two kind of things from other kind of areas of physics, such as Bose-Einstein condensation and the Laughlin state. And so they're both kind of realized as equilibrium states, one of bosons, the other is usually of fermions. But basically, they rely on kind of particle conservation to let us kind of fill up, the some levels in the bosonic system and then in a fermionic system. So as I understand, like naively, at least there is no particle conservation of photons fundamentally. So should I think of those states when they're realized with photons as highly non-equilibrium states, or is there some way to kind of induce conservation of photons, some chemical potential for them?
Alexander, there are the two religions. One is the religion of the ones who are putting a lot of effort in trying to optimize the lifetime of photons, making them as long-lived as possible. So then particle conservation is reasonably ensured, and then you can apply the standard methods of Condmat. This is more or less what happens in some circuit QED experiments. Some of the Google QED experiments are based on this idea. And also some experiments on exciton polaritons in microcavities. The most recent ones rely on a new family of devices which have extraordinary mirrors such that the lifetime of photons is very long. So the physics is mostly an equilibrium one. Then there is the other religion, which is the non-equilibrium people, to which I would say myself I belong. where you try to not to have a non-equilibrium as an enemy, but as a friend. Try to use the fact that you are not conserving the number of particles to find a way for the photonic system to dynamically enter the desired quantum state. So then the quantum state will be driven a dissipative one with most likely different properties, like the ring in the Photon BC that I showed you at the beginning of the talk. Say this ring, this is a typical non-equilibrium behavior due to the fact that we are not conserving the number of particles. But the advantage is that if I'm designing well driving and dissipation, I can also avoid the problem of cooling down the gas. So if you follow a bit the literature on atomic gases, one of the big enemies now is the temperature, or the entropy if you prefer. So in order to cool the system down to a fractional quantum Hall level, you need to really go to very low temperatures. And now it's still difficult to find a system which is cold enough to be in the fractional quantum Hall limit. Here instead, in photons, you can use the same non-equilibrium mechanism, which is used to relax down, also to keep the effective temperature, whatever it means for a non-equilibrium system, low enough to be in the fractional quantum Hall state. So you see, it can be a dissipation can be a good friend for you if you are able to walk along hand in hand.
Okay, I see. I'm just not used to thinking about those physics as being realizable in non-equilibrium. So it's just, confusing for me how an Laughlin state can be a non-equilibrium state.
You see here, perhaps this can be a bit convincing, is this diagram. So this, the pumping, which is frequency selective, is a sort of chemical potential. So it likes to emit particles, it likes to emit photons in a state which is resonant with the emitter, but does not like to emit a photon in a mode which is too high energy. So it like a chemical potential. Chemical potential likes to inject particles if the one particle state is below the chemical potential, not if it's above. Here something similar happens. You go up to the target state, but then you cannot go further up because the many-body gap blocks you.
Okay, that makes sense. I see. May I ask another question? So for the KPZ kind of scaling, what is the exact quantity that obeys the KPZ equation? So is it like an actual time, time evolution of something that kind of accumulates, or?
It's the phase. So what, in normal KPZ is the position of the interface. Here is the phase at the different points. You see, there is a conceptual difference that perhaps you have realized, is that the phase is a compact variable.
Yes.
While the height is non-compact. So of course there is a difference in this, and it's something that we are trying to investigate in more detail. But if you consider, instead of the phase being from 0 to 2 pi, a phase which is unwound and can have any value, basically it's like the height of your surface.
Okay, I see. So basically, do you need to assume like small changes in the phase, so not to see the periodicity, or?
In a sense, this would be a kind of naive thing to it would be the same. The minimum that one can see is exactly what you're saying, that the small changes are KPZ, but it looks like KPZ is much more robust than that. That these 2 pi, the 2 pi compactness is not too much a disturbance. There are some analytical arguments by Leonie Canet and Anna Minguzzi who support this point, and some numerics. It seems to work, but it's still kind of very recent results.
Okay, I see. Thank you.
Thanks.
So any other questions? So yeah, let me ask a question myself. I have plenty of questions, but maybe let me just ask one or two. So, I mean, as you know, even in the pioneering work of Haldane, when he proposed to bring topological to photon, topological effect to optics, basically. So he wrote himself that it would be difficult, if not impossible, to use magnetic materials, right? And basically, the surprise in our experiment was that, I mean, it works, even if it is challenging. So there are some critics saying that the topological gap needs to be large. But what we found in some experiments recently on the quantum Valley platform is that actually, if you make the gap large, you favor multi-mode operation, because so there is kind of a competition between single mode operation and the size of the gap. So is this something you can comment on?
What I can comment is that on one hand, when you try to do an experiment like Haldane was planning to, so in the sense shine laser light on a system and looking for the topological edge state, the effect of having a small topological gap can make the things difficult, because you have to really aim well at that level. And that level, if for some reason the temperature fluctuates, you are lost, because you're no longer able to accord your laser exactly in the gap. You are a much more lucky man, because you are lasing. And lasing, you know that Charlotte-Towns is intrinsically a narrow line width. If you are able to let the system laze on the edge, you don't care about the size of the gap.
Yeah,
if the gap moves up and down because you are hitting the system, the topological edge mode will just follow. So in your experiment, you will not see a nice Charlotte-Towns line width, because you have fluctuations which are thermal and whatever. But still, you see a very nice topo laser operation, as you indeed do, because you really see the emission from the edge. Then the second part of your question, why having a big gap is less favorable for topological lasers, that's something which I'm not so surprised. But to have it really in quantitative terms, one should really look at what stabilizes the topological edge emission. You know the work that Matteo has done about using the frequency dependence. So your first experiment explaining why it's so stable on the edge is a kind of a mystery, because you have a great advantage in your experiment where you pump the whole system and not just the edge, as the HIFA people had to do. So you must have some other mechanism which stabilizes the edge. Most likely is that frequency dependence. And for some reason, with the bigger gap, the Valley Hall big gap, it does not work that well. And it's not. There are plenty of devils in the detail in the operation of these topo lasers. We can spend 3 nights discussing about all that can happen, and still a lot of work to be done. But
so maybe another quick question.
Yeah.
So I mean, I really like that comment you presented, locking a lot of particles in phase as being one of the ultimate goal of this area. So that is interesting to hear. So so what do you see as the main theoretical roadblock for making that happen, having a large mode area for a laser to get for high power, for instance?
I would say that is what you found in your Valley Hall problem, in the Valley Hall system. That the system at some point, in a kind of uncontrollable way, it starts emitting in a multi-mode way. So there are some instabilities which are present. Of course, they are much nicer than the ones of a non-topo system. So if you did a non-topo system, you don't go very far away. Perhaps the only strategy with a non-topo system which may work is your bound state in continuum idea, where you really have a Q factor which is extremely peaked in one mode. So that perhaps is the only strategy which may lead somewhere at the moment.
Okay, very good.
So, but now saying a topo laser is typically better, but still it's often multi-mode. And for us theorists, it's not really clear yet why in some cases it's multi-mode and why in some cases it's single mode. So we are trying to work out all different cases and trying to understand one by one.
Okay, very good.
So let's stay tuned
Okay,
to see if
indeed,
there is some
indeed.
answer.
So any other question? So if not, maybe I can ask one more. So you made one comment on the ring platform, saying that the insertion of the S shape to make the mode asymmetric, I mean emission asymmetric, was non-reciprocal. So I'm not sure I agree with that comment. No, it makes it asymmetric, but it doesn't make it non-reciprocal.
You're perfectly right. Boubacar was fast. It's still, it breaks parity, but it does not break time reversal at the linear level.
Mm-hmm.
But when you consider all the nonlinear dynamics of a topo laser, basically what happens is that the system has a sort of phase transition which breaks T. So it's a dynamic.
But that nonlinearity would also be present in conventional lasers, right? So why only in the topological case?
No, it's completely not related to a topo. Not related to topo.
Okay.
What is related to topo is that a topo system has two modes, going this way and this way.
Indeed. So but that non-reciprocity due to nonlinearities in laser, I mean, that was not shown in this experiment.
In here, it's not clear what they really showed, if there was really a single mode going in one direction. It's a bit ambiguous what they have.
Okay.
What I know, it's some unpublished result by Alberto, the new student, is that doing this kind of S-shaped device with some gain, then you basically cannot laser in the direction which would enter the S. So in this way, the system chooses one direction, which means that it breaks the effective pseudo-spin degree of freedom.
Absolutely. Okay, so in the interest of time, maybe if someone has a last question. So if not, I will ask.
I have one more question if there's time.
Okay, so last question then.
Okay, so I mean, it's kind of following up on one of the things that Boubacar just asked. So I'm trying to make connections to some of these concepts in classical nonlinear systems. For instance, at the beginning, you introduced the Gross-Pitovsky equation. I'm wondering, like, how much of this I need to invoke and how much of it can I describe by like a Kerr nonlinearity in a traditional nonlinear system?
Oh, you could describe everything in terms of classical Chi-3 nonlinearity.
Okay.
So basically, GPE is a way to reformulate the Chi-3 nonlinearity in a different language.
So I guess why are we using this language? Let me ask my question this way. Is it like, does it give new insights or?
Yes, yeah.
Okay.
At least it gives all the insight that people have accumulated in the quantum gases literature. So there was all the literature on superfluidity, which was completely disconnected from nonlinear optics, and making this link allowed to basically to use all those literature, all the insight that one had in that world. So myself, I was trained initially in nonlinear optics, but then I was a cold atom guy.
Mm-hmm.
So bringing these ideas of GPE equation into the world of nonlinear optics basically gave me the possibility of rereading well-known phenomena from a different point of view and understanding them in hopefully a deeper way.
Okay. Yeah, so in the interest of time, now let's stop here for PIs. So please leave the meeting now so that postdocs and students can interact more with Iacopo. Of course, if you have questions, feel free to reach out to him. Iacopo, thank you again for the fantastic talk. Okay?
Thanks a lot, Boubacar.
Yeah,
Thanks to all the PIs for being here. And really, I'm really looking forward to meet you in person, hopefully soon.
Indeed. Thank you.
Thanks.